In this video, we'll show that if we're doing random sampling, then the sample mean is an unbiased estimator of the population mean, and we'll derive the variance of the sample mean across possible samples. So there's a common setup to the two slides we'll do here. These are the values to be obtained from our random sample. Remember, x1 just stands for the value for like the first observation, x2 is the value for the second observation, and so on. The population has mean mu, variance sigma squared. This is the formula for the sample mean that you're familiar with. Notice all the x's here are capital letters. We're treating them as random variables. So the perspective here is before we do our random sample. All right, and what we're going to show is that for any sample size, the sample mean is an unbiased estimator of the population mean. Now remember what that means. It says that the average across possible samples we could take of our estimator is equal to the population parameter of interest. So in the unemployment rate example, if the true unemployment rate is 5%, we have to accept that some of our estimates will be higher than that, some of our estimates will be lower than that, just depending on who lands in the sample. But we hope that our process is correct on average. That is, across the possible samples we could have taken, we would get the population. On average, we'd get 5%. Okay. All right. So to do this, the first thing to do is we can drop in for x bar the formula up here, and you can see I've gone ahead and distributed the 1 over n coefficient out front to each of the x's. All right. And the reason I did that is we're going to use what we know about properties of linear combinations of random variables. So you saw a simple version of this going back to the portfolio problem, where an investor, invests in like a stock fund and a bond fund. Okay, so that was two random variables, x and y, and you saw this idea of linearity of expectation. You can distribute that expectation across the sum, and you can bring out the constants a and b. We're just going to do that for n random variables here instead of just two. Okay, so we distribute this expectation across the sum, and we also pull out the constants 1 over n in front of each of those expectations. This is done by linearity of expectation. There's nothing special, there's nothing else we need to assume in order to make this happen. Okay, that's just a property of the expectation operator. Now, what on average would be the value of x1? Well, x1 could be anyone from the population, and therefore its mean is the population mean. Okay, or in the unemployment rate example, if the true unemployment rate is 5%, then 5% of the time, the first person we talk to will be unemployed, okay? And so the mean of x1 is just 0.05. That applies to every other mean of a single observation here, x sub I, right? So it applies to the second person, the third person, all the way up to x sub n for the last person, okay? These all have the population mean, and you can see they're in such terms, so collecting them together, n times 1 over n times mu. Obviously the n and 1 over n cancel, and we just have mu. So this shows that the sample mean is an unbiased estimator of the population mean. Okay. All right, let's do the variance then. The setup is the same. What we're going to show is that for any sample size n, the sampling variance is, so this is the variance of the sample mean, treated as an estimator here, sigma squared over n. Okay, and here we're going to rely on another thing we learned about linear combinations of random variables. Okay, so remember, if you have variance of a relatively simple linear combination like this one, you can distribute the variance kind of, but it creates in general a covariance term. Okay, so the variance of this linear combination, a squared, variance x, plus b squared, variance of y. So you can distribute the variance across this, again, kind of. When you pull out constants a and b, they get squared because of the way variance is defined. And then you have a term that depends on the covariance of x and y, 2 times a times b times the covariance. Okay. All right, so let's see how this works. We're going to plug in, we're trying to find the variance here of the sample mean. This is our definition of the sample mean. Okay. Now, in general, we would have to find this variance, we would have to consider the covariance for every pairwise combination of the different x sub I. Okay. So there's like covariance between x1 and x2, covariance between x1 and x3, and on and on and on. But because under simple random sampling, our observations are independent of one another. They're all independent draws from the population. Then we don't have to deal with these covariance terms. All those pairwise covariances are 0, and those terms fall out. So we get a nice ability here to distribute the variance across the sum, in this case, without creating all those covariance terms. These 1 over n constant terms can come out. They get squared, 1 over n squared, 1 over n squared, etc. Okay. Now, just like on the previous slide, if you think about a random variable like x1, what is its mean? Well, it's just the population mean, because x1 has the population distribution. Well, because x1 has the population distribution, its variance is the population variance. And same for x2 and x3 all the way to xn. Okay? So now simplifying terms, we have n of these in this sum. And we can cancel that with one of the n's in the denominator there, and we get sigma squared over n. That's the variance. Okay? And the standard deviation, of course, is just the square root of that. So this is the population variance. This is the sample size. All right. Take the square root of that. You get the population standard deviation, sigma, divided by the square root of the sample size down here. All right. And what this means is, notice, this is true for any sample size, but it's also a function of the sample size. So in small samples, there's more variability in the sample means that you get from different possible samples. The larger your sample is, then a typical sample should look more representative of the population. There's less variability across samples in the values of the estimate that you could get. All right.